In this lecture, we're going to try to define the term distributed system. It won't be a perfect definition, but it'll be a definition that will work for us in this course. Before we do that, let's take a step back and define a different but related term, that is the operating system. What is the operating system? Well, if you've used a machine, if you've used a device, whether it's a tablet or a small phone, or whether it's a laptop or a computer or a server, all these devices, each of these devices runs an operating system, also known as an OS. So if you've used a computer, you've used an operating system. The operating system runs on the device and it manages the different components of the device. So before we define the term operating systems, let's name some examples of operating systems. Here are some names. Some OSs for big devices include Linux, Mac OS X, of course there are many different versions of it, Windows, of course again there are many different versions, and Unix and FreeBSD, and there are many examples of OSs for large devices, which I'm not listing here. For small devices like the handhelds and the tablets, you have operating systems like Android from Google, iOS from Apple, TinyOS, which runs on small sensor modes, which you'll see later on in this course, and of course many other small operating systems that I'm not naming here. Now let's try to define the term operating system. Before we jump to some well-known definitions, let's try to summarize what we know about operating systems. The operating system essentially provides a user interface to hardware. Your computer, any device, any computer consists of multiple devices. For instance, your computer consists of a keyboard, a mouse, a monitor, a hard drive, maybe multiple hard drives, and of course the CPU and the memory, and many other peripherals attached to the motherboard. All of these hardware pieces need to be managed, and these are managed by the software known as the operating system. The operating system runs a special piece of code for each of the devices that is attached to it. This piece of code is called a device driver. So essentially, as a user, you do not need to interact directly with these devices. It's very rare that as a user we think, oh, I'm clicking the mouse and now I need to worry about the message being sent from the mouse to the CPU. All of that is taken care of by the OS. The OS also provides abstractions. For instance, if you store your piece of code, you're rarely thinking of, hey, how does this code get stored as blocks on the disk? You're thinking of files, you're thinking of directories or folders. When you run your code, you're thinking of programs being instantiated as processes. You're not thinking of, where does this run on the CPU, where does it store memory, and so on and so forth. Those abstractions are provided to you by the OS. So essentially, the OS abstracts away the hardware-specific features and provides to users features that are understandable and usable by the users. The operating system, of course, has to manage these different resources that it is responsible for, which processes run when on the CPU, which files get accessed when on the hard drive, and so on and so forth. And of course, the OS is also a means of communication, whether it's sending and receiving email, or whether it's accessing the web, or just communicating in a distributed system. Here is the definition of OS from the Free Online Dictionary of Computing, also known as FALDOC. FALDOC defines an OS as the low-level software which handles the interface to peripheral hardware, schedules tasks, allocates storage, and presents a default interface to the user when no application program is running. Okay, so for instance, when you start up your machine and there's nothing running on it, the OS is running on it, so it's going to occupy the CPU. I won't go through the rest of this definition. You can read it by either pausing the video here or going to the FALDOC page online. But essentially, this definition seems to capture the characteristics that we said were true of operating systems in the previous slide. Now let's try to repeat the same exercise, but for the term distributed system. Let's name some examples of distributed systems. Here are some examples. A single client machine communicating with a server. For instance, if you know NFS, if you've used NFS, the network file system, a single client may communicate with a single server. That's a distributed system. A BitTorrent, which is a peer-to-peer overlay which consists of many millions of clients communicating with each other, is again another example of a distributed system. The internet, where you have many servers and clients and routers and switches communicating with each other, is another example of a distributed system. And the web, where you have servers and clients communicating amongst and with each other, is an example of a distributed system. Hadoop, which you'll study later on in the course, and data centers are all examples of distributed systems. What are not examples of distributed systems? Well, if you have a collection of humans, say in a party, interacting with each other, that's not a distributed system. Again, at least, that's not the kind of distributed system that we want to study in this course. They might be interesting, of course, in other courses, but not in this course. A standalone machine not connected to the network and with only one process running on it is again an example of something that is not a distributed system. Birds out there interacting with each other, that's again an example of something that is not a distributed system. It's an interesting I guess social phenomenon which biologists study, but not in a computer science course. So is there a good definition out there? Well, FallDoc, the free online dictionary of computing, was helpful to us with the OS definition. So let's go back to FallDoc for its definition of a distributed system. FallDoc says that a distributed system is a collection of automata. When it says automata, essentially it means programs whose distribution is transparent to the user so that the system appears as one local machine. It's saying that essentially the collection of machines appears as one machine rather than as multiple machines to the user who is using the distributed system. This is in contrast to a network where the user is aware that there are several machines and their location, storage replication, load balancing, and functionality is not transparent. Distributed systems usually use some kind of client-server organization. Okay, so this is the FallDoc definition for distributed systems. I claim that this definition is wrong. It's just wrong. And in fact, there are two mistakes in this definition. The first mistake is that the definition says that a distributed system, a collection of machines, appears as one local machine. Well, if this is true, then the web is not a distributed system. For instance, on the web, it's often the case that a website A may be up while a different website B is down, and at a different point of time, website B is up while website A is down. It's never the case that both A and B are up and both A and B are down. So essentially, these two web servers do not appear as one local machine, yet the web is a distributed system. The second mistake in this definition is the last sentence, which says that distributed systems usually use some kind of client-server organization. This is not always true. Peer-to-peer systems like BitTorrent and many other peer-to-peer systems before it rely largely on the clients communicating with each other. That's why they're called peer-to-peer systems. They do not rely on a server except for some very minor functionalities. Essentially, without the server, these systems would continue functioning just as normally. Okay, so, well, unfortunately, the FallDoc definition doesn't work for us. Well, let's look at a couple of definitions from textbooks. Andrew Tannenbaum, in his textbook on distributed systems, defines it as a collection of independent computers that appear to the users of the system as a single computer. Again, the same issue, the same error that we saw on the previous slide appears in this definition as well, so it doesn't work for us. Michael Schroeder, another famous distributed systems researcher, defines a distributed system as several computers doing something together. Thus, a distributed system has three primary characteristics: multiple computers, interconnections, and shared state. This definition is closer to what we want, but it's missing some components. For instance, it doesn't talk about servers or clients failing, and so that's a little bit worrisome here. So this definition doesn't work for us either. So all these definitions are short and they're looking inadequate to us, mostly because we are interested in the insides of a distributed system. We don't want to behave like users of a distributed system. We want to go under the hood. We want to go inside a distributed system and study what algorithms run there. How do you design a distributed system? How do you implement a distributed system? How do you maintain? And of course, what are the real characteristics of distributed systems? As you have seen, as I mentioned before, there are some examples that when you see it, you know that it's not a distributed system. Humans or birds interacting with each other, a standalone machine not connected to a network. So we know it when we see it, and this is captured very nicely in a quote by Justice Potter Stewart in a case in 1964, where he said that essentially, I know it when I see it, but it may be hard to define it. So we're going to venture forth a definition, and this is my working definition. This will work for this version of the course. So a distributed system, this definition says, a distributed system is a collection of entities, each of these entities being autonomous, programmable, asynchronous, and failure prone. And these entities communicate through an unreliable communication medium. Let me go through this definition and explain each of these adjectives here. The entities are essentially processes. Each entity is a process that is running on some device. Each entity is autonomous, meaning it's standalone. If left to its own devices, pun intended, if left to its own, it will run just fine. The entities are programmable. You have, of course, you have written code that is running underneath and inside these processes, so they are programmable. Notice that this is the term that eliminates humans or birds interacting with each other as being distributed systems. You can't really program human beings or birds. interacting with each other. So that's why those are not distributed systems. Asynchronous is very important. This essentially means that each process or each entity runs according to its own clock, and these clocks of different entities or processes are not synchronized with each other. They're not always showing the same time as each other. And you'll see a lot more about this later on in the course. And finally, each of these entities is failure prone. Each entity may crash arbitrarily at any point of time, and it may recover, for instance, at some point of time. And these entities are communicating through an unreliable communication medium whereby they send and receive messages through each other. However, these messages that are being sent may be dropped completely, or they may be delayed for inordinately long periods of time. Okay, so that's the definition that I have for a distributed system. So entity, when I say an entity, again, I mean a process on a device, be it a small PC, or be it a PC or a laptop, be it a tablet or a small sensor mode. And the communication medium may be a wired network or a wireless network or some combination thereof. So once again, the programmable adjective eliminates humans interacting with each other. The asynchronous adjective distinguishes distributed systems from parallel systems. Parallel systems include multiprocessor systems and supercomputers, where essentially very large numbers of processors share the same motherboard, or they're communicating with each other over a tightly coupled network, and they all have a synchronized clock. So all the processors are showing the same clock at all points of time. A distributed system is very different from that. A distributed system has asynchrony, which means that clocks are unsynchronized. And that's why distributed systems are harder to design algorithms for and implement for. You might remember a process which you've seen in the orientation lecture, a process in all its gory detail with its code, its stack, its program counter, pointing to where the code is currently executing, heap and registers, and a whole bunch of other things. Now, a process is an important entity in a distributed system. In fact, a distributed system, as we said, consists of many, many processes. In this example, I have 3 processes, P1, P2, P3, but there might be thousands of processes involved in a distributed system. You have an unreliable communication network involved underneath. In this course, we are not interested in the insides of the network, just the fact that you're able to send and receive messages via this network. So P1 might be able to send a message M to P3, which then gets delivered at some point of time to P3, and that receives the message. Okay, so this is essentially what we see as a distributed system. Multiple processes communicating by sending and receiving messages from each other. That's, when you think of the distributed system for working purposes for this course, that's really all you need to think about. Processes sending and receiving messages amongst one another. Caveat here, that's only a working definition good for this course. You should feel free to come up with your own definition for distributed systems. I would especially encourage you to try this exercise after you have seen the many, many examples of distributed systems as you see them in this course. So try it at the end of this course. So given this definition, there are many interesting problems for distributed systems, people like us, you and me. Peer-to-peer systems, which we'll study many of, cloud infrastructures, which we'll see some of, cloud storage systems, software systems, key value stores in NoSQL, we'll see some of those, Cassandra and HBase as well. Cloud programming, including MapReduce, Storm and Pregel, some of which you'll see soon. Coordination, including consensus protocols like Paxos, leader elections, snapshots, and many others. And of course, managing these many clients and servers that are interacting with each other via concurrency control techniques and replication control techniques. All these topics that I've listed on this slide are relevant to this course, and you'll see them as we move along in this course, both part 1 and part 2 of cloud computing concepts. When we solve these problems, we need to be aware of several features that are true in the distributed systems underneath, and we need to design for these features. Failures are no longer the exception, but rather a norm. As we've discussed before, when the scale of your system grows, failures become very, very common. When you have thousands of machines and terabytes of data, we need to be able to scale. Any algorithm you design for a distributed system needs to be able to scale very well to many, many machines and very large amounts of data. Asynchrony, again, is a very important challenge that you have to deal with when designing distributed algorithms. The fact that different processes have unsynchronized clocks means that you will have a difference between clocks, clock skew. You'll also have clocks moving apart from each other. That's known as clock drift. Again, you'll see these later on in the course. And of course, concurrency is something that you have to deal with. thousands of machines accessing the same data, interacting with each other, are bound to create race conditions and are bound to create conditions where data might be inconsistent. And so we have to be careful to make sure the data stays consistent even while machines are interacting with each other and are accessing the same data. So over the next few weeks, we will see several core concepts of distributed systems. Next week, you'll see gossip and membership. And then we'll see distributed hash tables as well, which are an important building block for peer-to-peer systems. And we'll alternate core concepts with the use of these core concepts in real systems. So when we see distributed hash tables, we'll also see their use in peer-to-peer systems. We'll also see how some of these building blocks are used in key value stores and NoSQL storage systems. For instance, these NoSQL storage systems use distributed hash tables, they use gossip, they use membership. That's why we study concepts first, and then we see how they're used in real systems.